This is the last video on forces. We will discuss how forces can cause objects to move in circles. Let's revisit Newton's first law. Newton's first law states that unbalanced forces cause acceleration. They can cause objects to speed up, slow down, or change direction. Here we have a moving asteroid. It feels no external force, so in accordance with Newton's first, it must keep moving in a straight line at constant speed. But suppose the asteroid comes close to this planet. The planet will start exerting a gravitational force on it. But the asteroid already has a component of velocity that isn't pointed directly at the planet. The planet cannot affect that component. In fact, the asteroid is traveling so quickly that it completely overshoots the planet. As it continues moving, the direction of the force keeps reorienting, pulling it toward the planet. But its velocity keeps making it overshoot. So it's never actually able to land on the planet. Instead, it orbits around it. The force that pulls toward the center of the orbit is called a centripetal force. Centripetal force isn't an actual force like weight, normal, tension, friction, or applied force. It's just the term applied to whichever one of those actual forces is responsible for creating the orbit. In this case, the gravity of the planet is the centripetal force. Now, let's look more closely at this geometry. The velocity of the object always points tangential to the orbit, but the force always points toward the planet. And since we know from F equals ma that total force and acceleration always point in the same direction, that means acceleration always points toward the planet. In this special instance, the velocity vector and the acceleration vector are 90 degrees apart. You'll remember from the early kinematics videos that when velocity and acceleration are in the same direction, the object will speed up, and when they're in opposite directions, the object will slow down. But what about when they're at 90 degrees? At 90 degrees, the acceleration cannot change the size of the velocity vector, only its direction. So the asteroid moves to this location. The direction of the velocity has changed, of course, but we see that the direction of the force, and therefore the direction of the acceleration, has changed as well, because the asteroid is now in a different position with respect to the planet. The angle between the velocity and acceleration is still 90 degrees. So once again, the acceleration changes the direction of the velocity vector, but not its size. And this process keeps recurring. The acceleration keeps bending the velocity, and as the object moves in response, the acceleration keeps redirecting to stay at 90 degrees from the velocity. This is uniform circular motion. In uniform circular motion, the size of the velocity never changes, only its direction. But for this to occur, the acceleration has to have a very specific value, given by this equation. The size of the centripetal acceleration must be equal to the size of the velocity squared divided by the radius. We will explore this in the following examples. Consider this animation. Here we see a nail in the center of a frictionless table. A 3-kilogram object is connected to the nail using a rope, and it travels in a circle with a radius of 0.5 meters. Its speed is constant at 1 meter per second. What is its acceleration, and what is the tension in the string? We'll start by drawing a picture. This is a side view of the object when it is at its furthest left position. We're seeing the table edge on. We have a special name for this type of motion. When an object is moving in a circle but its height isn't changing, we say it is following a horizontal circle. Now, let's draw the free body diagram. In the y direction, there is weight and the normal force, and in the positive x direction, there is tension. We'll focus just on the x direction. The total force in x is represented by the tension. This in turn is equal to mass times acceleration. But for an object in uniform circular motion, we can solve for the acceleration. It's equal to v squared over r. In this case, that works out to 2 meters per second squared. We can use this information in the force balance to work out the tension. It has a magnitude of 6 newtons. This is the centripetal force required to keep the object moving in a circular path. This is a variant. It's called a conical pendulum. Again, the bob is tracing out a horizontal circle. Consider this situation. A 1 kilogram conical pendulum is tracing out a circle 0.1 meters in radius. The tension in the string is 15 newtons, and the string makes an angle of 25 degrees from the vertical. What is the velocity of the bob? Again, we will examine it at its leftmost position, and again, we will start with a picture. The free body diagram contains only 2 forces. The weight force pulls it down, and the tension force supports it. But the tension force is at an oblique angle. We need to break it into its components. Since the angle of the string is 25 degrees from the vertical, then the other angle above the x-axis is 55 degrees. When we break it into its components, we get a free body diagram that looks a little bit like the last example. There's a vertical component, t sine 55 degrees, and a horizontal component, t cos 55 degrees. Now, let's analyze the force in the x direction. The only force present is the horizontal component of tension, so that must be equal to mass times acceleration. We substitute for everything we know, and we find the value of acceleration. It is 8.6 meters per second squared. This is the centripetal acceleration, and it's equal to v squared over r. Substituting in for r, we find that v is equal to 9.28 meters per second. A vertical circle is one where the height of the object is changing. In these cases, there can be multiple forces contributing to the centripetal force, and the velocity is generally not constant. An example is the famous trick of whirling a bucket of water over your head without the water spilling out. Consider this question. A 5 kilogram object is swung on a 0.75 meter rope. What is the minimum velocity it can have at the top if it completes the circle? We start off by drawing a picture. Now, what are the forces at the top of the circle? Clearly there's weight, that's unavoidable. But how big is the tension? Well, in circular motion, acceleration is related to velocity. If we're talking about the minimum velocity, that must yield the minimum acceleration, which in turn means the minimum centripetal force, which means besides weight, there can be no other force at the peak. So the free body diagram contains weight. That's it. Let's do the force balance in y. The total force in y is now just the weight force. That's equal to mass times acceleration. We can easily solve for the weight force. It's 49.05 newtons. Set this equal to mass times acceleration and solve for the acceleration. We get an acceleration of 9.81 meters per second, and this makes sense because at this point the object is feeling only one force, gravity. But this acceleration is in turn equal to v squared over r. Since r is 0.75, we can solve for v. It is 2.71 meters per second. This is a legitimate way to solve this puzzle, but in a few videos we'll see a much easier way to solve it using work and energy. When you take an exit off the I-95 onto a smaller road, you often have to take a circular off-ramp. Have you ever noticed that the off-ramp is tilted? Here, the normal force from the road is providing an assist as you move in a circle. This is known as a banked curve, and it combines concepts from ramps and circular motion. Consider this situation. You are in a 1,000 kilogram car. You are on a circular off-ramp with a radius of 100 meters. It is banked at 5 degrees. What is your velocity? We start by drawing a picture and a free body diagram. We see there are only two forces, weight and normal force. This is the only ramp puzzle where we set the axes in line with the weight, not the normal force. When we do so, we see the normal force at an oblique angle, 5 degrees to be exact. So we have to break it into its components, and we see the logic for not tilting the axes as in other ramp puzzles. The normal force is responsible for the object moving in a circle. It is the centripetal force. So we must have a component in the x direction for it to operate as such. We'll set up the force balance in the y direction. The total force in y equals normal cos 5 degrees minus weight. The weight is easily found. It is 9,810 newtons. Applying this in the force balance, we can solve for the normal force, 9,847 newtons. What about the x direction? Well, the only force in x is normal sine theta. We substitute the normal force in and solve for the centripetal acceleration, 0.858 meters per second squared. Finally, the centripetal acceleration equals v squared over r. So once again, we substitute for what we know, and we get a velocity of 29.3 meters per second. In this video, we saw several examples of circular motion and the centripetal force that causes it. This concludes our discussion of forces. In the next video, we will begin a new chapter, work and energy.